Now let's just move on further and talk about some of the problems that are all related with the Pythagoras theorem and the converse of the Pythagoras theorem. So the very first question says that PQR is a triangle right angled at P and M is the point on QR such that PM is perpendicular to QR. We have to show PM square is equal to QM into MR. So let's just draw the figure for this one first. It says PQR is a right angled triangle at P. So let us suppose if I am taking this triangle in such a manner, so this is nothing but P and this is nothing but Q, and let us suppose if I'm taking it as R, this is right angled at P, and further it says that M is a point on QR. M is a point on QR. So M is actually a point which is lying on the hypotenuse of this particular right angled triangle such that PM is perpendicular to QR. It says PM is perpendicular means this PM is perpendicular, this PM is perpendicular to this QR, and we have to show that PM square is equal to QM into MR. So let's just start the proof of this particular question. So first of all, we'll say that we will use a particular theorem over here that we have used for the proof of the Pythagoras theorem. So we know that if a perpendicular is drawn, from right angle of a right angled triangle on the hypotenuse, then the two triangles so formed are similar to each other and to the whole triangle. So we know about this theorem. So using this theorem, we can say that if a perpendicular is drawn from the right angle of a right angled triangle PQR on the hypotenuse, as we can see over here, on the hypotenuse PM, then the two triangles so formed, they are similar to each other. So it implies that using this particular theorem, we can say that the triangle PQM is actually similar to the triangle PRM. So if these two triangles are actually similar to each other, then we can say or we can use the area of the similar triangle theorem, that the area of the triangle PQM by the area of the triangle PRM is equal to the square or the ratio of the squares of their corresponding sides. Means we can say this would be nothing but PM by RM whole square, and we are using the theorem area of similar triangle over here, that if the two triangles are similar to each other, then we can write the ratio of the areas of the two similar triangle is equal to the ratio of the square of their corresponding sides. So using that concept, we can write this thing over here. Now let's just further talk about the areas. So as you can see, we have the area of triangle PQM, area of the triangle PQM. So what can we say about this particular area? This would be half into base into height. What would be the base of this particular triangle? This would be nothing but QM. So this QM into height. What would be the height of this one? This would be nothing but PM. Now further, we have the area of the triangle. The triangle is nothing but PRM. So the base of this particular triangle would definitely be nothing but RM. So this would be half into RM into height. Height is again PM, which is nothing but is equal to PM square divided by RM whole square. So let's just cancel out the values, whatever are cancelling over here. So we can see half and half are getting cancelled, PM getting cancelled. We have QM by RM, which is nothing but is equal to PM whole square by RM whole square. So let's just take this RM toward the other side. So this would be nothing but PM square is equal to QM into RM whole square divided by RM. So one RM get cancelled with one RM, we are left with only one. So at the end we are getting PM square is nothing but is equal to QM into RM, and that is what we have to prove, that PM square is actually equal to QM into MR or RM. So this is nothing but the proof of this particular question using the Pythagoras theorem and the theorem of the area of the similar triangles.